Hi all, this is Ade from IE Lion Academy, and I want to quickly go over this algebra and drawing graphs set of problems. Part A, it says that on the same axis, it asks us to sketch the graphs of the curves with equations y equals x squared in brackets x minus 2, and the second equation or function is y equals x brackets 6 minus x, and we are being asked to sketch the curves. Now my method for this is to think of critical points or critical values, i.e. If you imagine drawing graphs as joining dots, then you need dots which represent something important to the function or to the curve. The critical values that I usually base my method around are the y-intercept, the x-intercepts, and the turning points, so wherever the graph changes directions, and I call these critical points, and there are straightforward methods to figure these critical points out. So we'll start with expression number 1, y equals x squared x minus 2, and the first thing I've done is write it out. Now, in order to find the x-intercepts, we have to make y equal to 0, or we have to figure out which values of x would make y equal 0, because you touch or you cross the x-axis when y equals 0. So here I've basically confirmed that y equals 0 when x equals 0, because 0 squared multiplied by anything is going to equal to 0, and when x equals 2. So 2 minus 2 in the brackets is going to be 0, and 0 minus multiplied by anything is going to be 0. So I basically confirmed that the x-intercepts occur at the coordinates 0, 0 and 2, 0. Now I find the y-intercept. Now the y-intercept, you cross or you touch the y-intercept when x equals 0. And when you plug x equals 0 into this equation, y equals 0. So we can confirm that the y-intercept is at 0, 0, which is also the origin. Now, in order to find the turning points where the graph turns direction, where there are humps, peaks or troughs, we need to expand and differentiate to find the turning points. So basically multiply out the brackets is what I mean by expanding. So here I've multiplied out the brackets, and then I found the first differential of this expanded equation. Basically the change in y over the change in x will give us the gradient, and we want to find at which point is the gradient equal to 0, because when the gradient is equal to 0 there is a turning point. That tells us that the graph has stopped increasing or decreasing and is about to change direction. So this is why I have a note here, turning point when dy over dx equals 0. So I set my differential to 0, and I basically solve the quadratic to find the solutions of it. So for the left side to be 0, what values of x must we have? And I can confirm that x equals 0 and x also equals 4/3. So it is at these values of x that we have turning points. Now we've got the x values, we also need the y values, because the x values plus the y values gives you the entire coordinate. So we need to take these values and plug them back into our original expression to find out what the y value is. And I'm doing that here. So here is our original expression. Let me just confirm that. Yes, here is our original expression. And when x equals 0, y equals 0, so we have a turning point at the origin. And when x equals 4/3, y equals minus 32 over 27. So the coordinate here is 4/3 minus 32 over 27 for the other turning point. In this white space here, I have the actual graph drawn, but I'm not going to show it yet because we also need to draw the other expression, because the question asks us to also sketch the curve of y equals x, 6 minus x. Now that's more simple because it's actually just a quadratic. So once again, with our same methods, we find the critical values. We find the x-intercepts, the y-intercept, and the turning point. So for the x-intercepts, I basically have to figure out what values must x be for y to equal 0, because that's when you touch or cross the x-axis for the x-intercepts. So I've confirmed here that when x equals 0, y equals 0, so we have one x-intercept there. And when x equals 6, y also equals 0, so we have one x-intercept there. So the x-intercepts occur at the coordinates 0, 0, and 6, 0. Now to find out what the y-intercept is, I basically plug in x equals 0 because you get the y-intercept when x equals 0. So when x equals 0, y also equals 0, so we can confirm again that the y-intercept occurs at the origin, 0, 0. To find out the turning point of the graph where it changes direction, I expand and differentiate to find the turning points by setting my first differential to 0. So here I've taken my original expression, expanded it out, and set my differential to 0, and therefore I solve the quadratic. Okay, so here I have found a solution where the differential can only be 0 when x equals 3. Then I plug this value into my original expression to find out what y should be, and that gives us the coordinate of the turning point. So we have our coordinate of the turning point 3, 9. And so here is me basically drawing both graphs. So I've got my my first expression, x squared x minus 2, and that is a polynomial. So polynomials are characterized by having a maximum of 2 turning points. And then my second graph in blue, my second sketch in blue, is the quadratic, and quadratics are characterized by having 1 turning point. Okay, now our second question, part B, says use algebra to find the coordinates of the points where the graphs intersect. Now if we look on the graphs here, we can see that the graphs intersect at 3 points. This one here, this one here, and this one right here. So let's go ahead and do that. Let's go ahead and solve that. So here I've basically confirmed that graphs intersect when they equal each other at certain coordinates. By extension, that means that graph intersects when their functions equal each other. So if we label the first graph as 1, or the first function as 1 and the second function as 2, we basically have to set 1 equal to 2 and then solve it for which x values are required for them both to equal each other. So I have set both equations equal to each other, or functions equal to each other. I have expanded and I'm just cleaning up. And here I have a third order polynomial. Okay, now this next part is literally just long division. So we have to solve this polynomial using long division. Now the first step to polynomial long division is to first guess at least one factor. You need at least one factor, and then you basically divide the polynomial by that factor to get the other factors. All I've done is just guess that this becomes 0 when x equals minus 2. So when x equals minus 2, the left hand side equals 0, which makes the right hand side also equals 0. Okay, so that therefore means that x plus 2 is a factor. X plus 2 is a factor. And then I've done polynomial long division here. I will probably make a longer video on how to do polynomial long division easily, but in this video I'll not do that because it would make the video too long and we would be tackling too many concepts. The concept of this video is to simply sketch curves accurately. So basically here I figured out that the other factors of the polynomial are x minus 3 and simply x. So if you were to multiply all of that together, multiply out, you would end up with the original polynomial right here. Now it gets a bit different here because we are not finding x-intercepts. Okay, what we are doing is that we are finding solutions. So x-intercepts, y-intercepts, finding solutions, they're very interchangeable depending on the situation or the context. In this context, we're not trying to find where the graphs or where the line crosses the x-axis or the y-axis. We're trying to find a solution to where the graphs equal each other or where the functions equal each other. Doing polynomial long division here and finding 3 factors tells us that the graphs cross or intersect each other when x equals 0, minus 2 and 3. Now in order to find the y value and therefore the entire coordinate, we have to plug these values into either equation 1 or 2. So I take my 0, my minus 2 and my 3 and I plug it into either equation 1 or 2. The simplest equation is equation 2. So we plug in 0, minus 2 and 3 into there. So I choose 2 and I basically just go through the motion. So when x equals 0, y equals 0, so the first intersection is at the origin. When x equals minus 2, y equals minus 16, so the second intersection is at minus 2, minus 16. When x equals 3, y equals 9, so the third intersection is 3, 9. And here I've just typed both equations or both functions into Desmos graphing calculator, and I basically confirmed that they cross or intersect at these 3 points. And also I basically confirmed the shape of my original sketch. Okay. Last but not least, the third question is basically just a plenary question to make sure that we understand how to sketch curves, especially with polynomials. Okay, so part C asks us to sketch the curve y equals x cubed plus 2x squared minus 5x minus 6, indicating the coordinates of the points where the curve crosses the y-axis, the x-axis, and all turning points. So this is basically telling you find the critical values and use those to sketch the curve. So if we go down to our solution right here, I start with my expression and I guess a solution for x, because we can't, this is a third order polynomial. We can't really solve this easily unless we have at least one factor or one solution. I guess that when x equals minus 1, the right side equals 0. Equals 0, so that means that x plus 1 is a factor, because x plus 1 equals 0. Then, using this one factor, I use polynomial long division to find the other factors. And this is my answer to that. So I basically reduced this third order polynomial into this multiplication of 2 functions, x plus 1 and x squared plus x minus 6x. X squared plus x minus 6x is a quadratic, and that's quite straightforward to solve, because solving a quadratic by factorization involves you finding 2 numbers that multiply to give a c but add up to give b, where a, b, and c simply relate to the coefficients in front of the x. So the only 2 numbers that do that are 3 and minus 2, because 3 times minus 2 gives you minus 6, but 3 plus minus 2 gives you 1. So I've substituted 3 and minus 2 into my 1 there, and I've basically solved the quadratic to get my 2 final factors, x minus 2 and x plus 3. So I have been able to turn this third order polynomial into a multiplication of 3 factors, x plus 1, x minus 2, and x plus 3. So to confirm the x-intercepts, what values of x would make y equal to 0? Because remember, you cross the x-intercept, you cross the x-axis when y equals 0. And for that to happen, x equals 1, 2, or minus 3. So we've confirmed the coordinates of the x-intercept. The y-intercept is clearly minus 6, because if we go to the original expression, the only thing left standing when x equals 0 is minus 6. Remember, the y-intercept occurs when x equals 0 as you're crossing the y-axis. So we have confirmed here that the y-intercept is 0, minus 6. In order to find the turning points, we differentiate and we set our first differential equal to 0 to find the turning points. Now, when we made our first differential, we got this this quadratic. We can't solve that using factorization. We therefore need to use the quadratic formula, which I've written in purple here. It's a very straightforward formula to follow. It just uses the coefficients a, b, and c, and we find out that the solutions to this quadratic are x equals 0.786 and x equals minus 2.12. We plug these values back into our original third order polynomial to find out what the y value would be, and that will give us our coordinates of the turning point. So we find out that we have turning points at this coordinate here and this coordinate here. And here's me basically attempting to draw out the expression, the third order polynomial. The only thing I haven't done is mark the coordinates here, but if you were to plug this into Desmos, you would be able to confirm that these points are all accurate. So I hope this long, I said it was going to be short, it turned out to be more than 10 minutes. I hope that this video has been very instructive and very educational, because in my time teaching maths, I've realized that students have struggled with curve sketching. Curve sketching is the beginning of really playing around with these functions and finding solutions to these functions. When you're given a function, the primary solution is just what it looks like. Once you understand what it looks like, then you can understand what it does and how it interacts with other functions. But you won't be able to do that if you cannot at least find solutions to the function enough to draw what it looks like. So once again, I hope this is instructive. Try it out in your own time. Like, subscribe for more videos, and I'll see you guys in the next one.